In this lecture, we'll take a look at some examples of analytic functions. So perhaps the simplest kind of example are just polynomials then. These are, of course, analytic. You can also consider quotients of polynomials, that is, rational functions, like this. And they will also be analytic, except possibly for the zeros of the denominator then. And then we also have the complex exponential function, which can be defined if we put z equal to x plus iy. We can define this, if we like, as e to the x times the cosine of y plus I times the sine of y, like this. So in this way, you define the exponential function completely in terms of well-known real-valued functions. It's also possible to define the complex exponential function as a power series, like this. In many respects, this may be a better definition, and we'll come back to that later on then. And once you have the complex exponential function, you can also introduce the trigonometric functions by using Euler's formulas. So, for example, the complex sine function is defined as e to the I z minus e to the minus I z, and then divided by 2i. And the complex cosine function is similarly defined as e to the I z plus e to the minus I z, and then divided by 2. And then you can, of course, go on to define the tangent, complex tangent function as a quotient of this, and so on. And so far, these are all quite natural and simple complex functions which are analytic then. The next step, however, is a little bit more tricky, because now we want to introduce the inverse of the complex exponential function, that is, the complex logarithm. So if we recall that in real value theory, we define the logarithm of a number as the unique root of an equation like this. So given a positive number y, we define the, say, natural logarithm then as the unique solution of this equation. And then we can try to do the same thing in the complex setting now. So we want to define the complex logarithm of z to be the solution of this equation. However, here we have a problem now. And the problem is that this complex exponential function is not injective, which means that this equation will always have many solutions, except for the one case when z is equal to 0, when it will have no solution at all. In fact, if w is a solution to this equation, then also w plus 2 pi ki will be a solution for any integer k. Well, so how should we proceed then? Well, let's have a look at what the solution will be here now. If we write z in polar form, like r to the I r times e to the I theta, and then put this equal to e to u plus iv. So we have put w equal to u plus iv then. Then by just factoring this, we see, of course, immediately that r must be equal to e to the power u, and theta must be equal to v. But of course, we have this ambiguity here now, so we can add any integer multiple of 2 pi, and we still get a solution. So here we see now that, of course, that u must be the ordinary real logarithm of absolute value of z. So if we try to write down a definition of the complex logarithm, then the real part here will be no problem. It must be simply the ordinary real logarithm of absolute value z. But then we also see that the imaginary part, that is v here now, can be any argument for z. So let me write this as argument of z, with this now, so to speak, symbolizes all possible arguments for the complex number z. So actually this can be taken as the definition of the complex logarithm of the number z. And it has most of the nice properties that a logarithm should have. The problem is that it's not really a function as it stands. It's what you can call a multi-valued function. So you cannot always treat it as a function in the way we are used to. And this is simply because this argument then is also multi-valued. So if you really need to treat the logarithm as a function, what you have to do then is to make some kind of choice. You have to decide what argument to use. And the most common choice then is to use what's called the principal argument, which by definition is the argument which lies in the interval from minus pi to pi, where we have equality here then. So for every complex number, you can choose an argument then in this interval, and that's called capital A argument then, or the principal argument function. And then we also define the principal branch of the logarithm function to be, well, first this real part here, which was unproblematic, and then plus, oh sorry, this should be an I there, and then plus I times the principal argument of z. So this is now a well-defined function, but it has its problems also. So for example, if we consider the complex plane here now, we will see that the principal branch of the logarithm function is defined everywhere except at the origin. But it will have discontinuities along the negative part of the real axis. So if you sort of approach the negative part of the real axis from above here and measure the principal logarithm, then it will make a jump down by 2 pi I then here whenever you pass the negative part of the real axis from above to below them. And also you should remember that the ordinary logarithm laws will not always be satisfied. For example, you cannot be sure that the logarithm of z square should be equal to 2 times the logarithm of z. This can be it could be right and it could be wrong. Actually, it turns out to be correct if you're in the right half plane, but it's wrong in the left half plane. So the conclusion from all this is that in many situations we will use this principal branch of the logarithm function. In some cases we'll just keep to the multi-valued logarithm function like this. And remember that this represents then many values. And occasionally we'll also use different branches, other branches of the logarithm function. For example, we can find a logarithm function which is continuous in all this part, but not on the positive real axis. Or we can find one which is continuous here, but not on the lower part of the imaginary axis. So according to what problem we are discussing, we may choose different branches of the logarithm function then. The logarithm function is important for many things. One of the immediate things that we'll need it for is that we also want to define powers, complex powers like this, z to the power alpha. If alpha is an integer, of course, this is there's no problem about this. If you have z to the power 3, then this is just z times z times z. But the problems will arise when this is not an integer. In this case, the way we can define this complex power is to use actually the exponential function and the logarithm function. And so we can write this as e to the power alpha times the logarithm of z then. So here I have used the multi-valued logarithm function, which then means that this can take many different values. So if you just write z to the power alpha, it's not a unique complex number, even if z and alpha are determined then. So it depends on how you choose your logarithm. So just to illustrate this, let us consider as an example what is I, the complex unit, to the power I. Well, according to our definition, then this should be equal to e to the power I times the logarithm of I. So what is the logarithm of the complex unit then? Well, the absolute value of I is 1, so the logarithm, the usual logarithm on that is 0. So the real part of this expression is then 0. But then you have the imaginary part, which is I, and if you take here, for example, the point I, we see that the argument here now will be, for example, pi divided by 2. But we can also add any multiple of integer multiple of 2 pi. So these are the possible values of this multi-valued logarithm function at the point I. And if you insert this here, you see that we get e to the power I times pi divided by 2 plus k 2 pi. And now, of course, I times I, that will just be minus 1. So we see now that we get these possible values here now, where k is just now any integer. So the next example we want to consider is the inverse sine function. Actually, you can do the same thing for the other trigonometric functions, but I take this one as an example. So what we want to do is to solve really the equation sine of w is equal to z. And remember, the sine function can be written as 1 over 2I times e to the power iw minus e to the power minus iw. So if you now just formally solve here now for w, then it looks like as follows. We multiply by this factor 2I and rearrange a little bit, and then we get e to the power iw minus, and then we write this as 1 over e to the power iw, and this will then be equal to 2I z. And then we see that this is really a second order equation for this exponential here now. So if you multiply by the exponential, we get e to the iw square minus, and we get a 1 here, which we move to the other side, and this term here will then give us 2I z times e to the iw, and then we have 1 here. And if we now complete the square, we see that we get e to the iw minus I z square is equal to first the 1 here, and then we have added the square of this term, which will then be I square minus times z square, so minus z square here. And then we formally, so to speak, take the square root of both sides here now, which means raising to power 1/2, and in addition, we move this term over to the other side, and we get the expression e to the power iw is equal to I z, and then say plus square root of 1 minus z square, like this. And then we can, of course, solve now for w by taking logarithms of both sides and divide by I. So we get that w is actually equal to 1 over I times the logarithm of, and let's write them in the other order, 1 minus z squared to the power 1/2, and plus I times z, like this. So this, what we have here, is really now a formal expression for the inverse sine function. But of course, it involves this multivalued logarithm here, and we also have to make a choice here when we define this square root. So it's not really uniquely determined as it stands here. However, fortunately, it turns out that if we use the principal branch of the logarithm function to here, and also if we use the principal branch of the logarithm function to define the square root, then this will reduce to the usual arcsine function for real z in the interval between -1 and 1. So we'll actually see that this is a natural generalization of the ordinary arcsine function. So for this purpose, then let z be equal to x, and we suppose that x is between -1 and 1 then. So what will this expression be then? Well, w will be equal to 1 over I, and then we get, we have the principal logarithm then of 1 minus x squared, and square root of that, and plus ix here now. And first we observe here now that for x in this interval, 1 minus x squared will be a positive real number. And if we take the principal logarithm of that, that will also simply be the a real number, the ordinary logarithm then. And this means that this square root will just be the usual square root of, so we can actually write this as 1 over I times principal logarithm here now of square root of 1 minus x squared, and then plus ix, like this. And now we must compute this logarithm here now. So how do we do that? Well, first we observe that the absolute value of this complex number here is equal to 1. Because if you take the square of this, you get 1 minus x squared. And if you take the square of this, you get x squared. And if you add them, you get 1. And this means then that the real part of this expression, which is the ordinary logarithm of the absolute value of this, that will just be 0. So we get 0 plus, and then we get I times the principal argument of this number here now. And so what is the principal argument of this? Well, let us just draw this point in the complex plane. Here we have the unit circle, and so this will, for x in this interval, this will actually give you a point on the right half of the unit circle. So suppose it's this point then. Then you see now that the vertical coordinate, the imaginary part here, is just x. And since it's a unit circle, this will be 1. And this part here is, of course, 1 minus x squared then. And the argument of this number here now, the principal argument, is just this angle. And what do we know about this angle from trigonometry? Well, if you take the sine of that angle, you get x divided by 1, that is x. So the angle here must simply be the arc sine of x. So this is really the arc sine of x now. And then you see that these two i's here will cancel out, and we're just left simply with the arc sine of x.